Hello everyone, this is Mystery Club. This video takes you to see the largest stars in the universe. First, as everyone knows, the closest star to us is the Sun. The Sun's diameter is approximately 1.39 million kilometers, and its volume is about 1,000 times that of Jupiter, 21,000 times that of Neptune, and 1.3 million times that of Earth. At first glance, the Sun seems like a very large star, and indeed it is, but only within our solar system. If we look at it on the scale of the Milky Way galaxy, or even the entire universe, it is actually very ordinary and not large at all. Within the Milky Way galaxy alone, there are many stars larger than the Sun. For example, Sirius A. Why emphasize A? Because Sirius is actually a binary star system, composed of two stars, Sirius A and Sirius B. Sirius A is a main sequence star, and Sirius B is a white dwarf. Therefore, the light we see from Sirius at night is entirely emitted by Sirius A, which is also the brightest star visible to the naked eye in the night sky, while Sirius B is invisible to the naked eye. Sirius A is relatively close to us, only 8.6 light-years away. Its diameter is approximately 2.38 million kilometers, 1.7 times the diameter of the Sun, 5 times its volume, and 2 times its mass. Arcturus, another relatively close star, is about 36.7 light-years away. Its diameter is 25.4 times that of the Sun, and its mass is 1.5 times its mass. Betelgeuse is 863 light-years away, with a diameter 79 times that of the Sun and a mass 18 times its mass. Betelgeuse, the star that looks like it could explode at any moment, is about 640 light-years away. Its diameter is 887 times that of the Sun, and its mass is 20 times its mass. So, all these stars are larger than the Sun, but except for Betelgeuse, the others aren't so large that the Sun is invisible. However, the stars we're about to look at are so large that the Sun is practically invisible compared to them. WOH G64, a red supergiant star located 5,900 light-years from us in the Milky Way, was first catalogued in 1860 by German astronomer Friedrich Agland. A few years ago, it was considered the largest star by volume, and even now, it's likely the first star many remember. Scientists calculated its diameter to be approximately 1,700 times that of the Sun, and its volume to be about 5 billion times that of the Sun. To put this into perspective, light traveling at 300,000 kilometers per second could circle the Earth 7.5 times in 1 second, but it would take 14.6 seconds to circle the Sun's equator. If light were to travel at the speed of light around the equator of WOH G64, it would take nearly 7 hours. However, this data is from several years ago. Recent calculations show that its size was overestimated. After recalculation, its diameter is approximately 910 times that of the Sun, and its volume is about 750 million times that of the Sun. If it were placed in the current position of the Sun, it would engulf all celestial bodies within Jupiter's orbit. From this perspective, although its recalculated size is much smaller than before, it's still quite enormous. Current research suggests that WOH G64 has only 10 to 50 million years left to live. Generally, stars become white dwarfs after exhausting their energy. If the mass of its remaining core exceeds 1.44 times the mass of the Sun, remember what 1.44 is? It's the Chandrasekhar limit, which we discussed in the black hole video. It will continue to collapse, becoming a neutron star. Neutron stars have extremely high densities, with a mass roughly 1 to 2 times that of the Sun, but a radius of only 10 to 20 kilometers. If the mass of its remaining core exceeds 3.2 times the mass of the Sun, gravitational collapse will continue, eventually leading to a black hole. Stephenson 2-18 in the past few years has been considered by many to be the new largest star, surpassing WOH G64. Scientists calculated its diameter to be approximately 2,150 times that of the Sun, its volume to be about 10 billion times that of the Sun, and 130 quadrillion times that of Earth. Light would take nearly 9 hours to orbit it. If placed in the Sun's position, it would engulf all celestial bodies within Saturn's orbit, including Saturn itself, and would also scorch Uranus. However, in recent years, more and more people have questioned the size of Stephenson 2-18 because it exceeds the Humphreys-Davidson limit. This limit was proposed in 1979 by astronomers Roberta Humphreys and Chris Davidson. Simply put, they believe that there is an upper limit to the luminosity of massive stars, like a ceiling on their brightness. When a star becomes extremely bright, it becomes unstable because its luminosity is too high, causing it to lose all its matter. At this point, it will use stellar winds to blow away matter, thus reducing its brightness. In other words, the brighter a star is, the easier it is to lose matter. Looking back at Stephenson 2-18, a star of its size shouldn't be able to maintain both high luminosity and large volume simultaneously. It should lose matter through stellar winds, becoming less luminous. However, its luminosity is extremely high, approximately 440,000 times that of the Sun, and its volume is also enormous, completely violating this limit. It's much brighter and larger than we expected. This paradox suggests that either the limit is wrong, indicating a problem with our understanding of stars, and they might genuinely grow to such a large size while maintaining such high luminosity, or we have overestimated its size. Measuring the size of a large star like Stephenson 2-18 is very difficult. Firstly, it's extremely far away, about 20,000 light-years from us. Secondly, its location is relatively close to the center of the Milky Way, surrounded by countless other stars, making it difficult to measure its true luminosity. And thirdly, the outer atmosphere of such a red giant is much more diffuse than that of stars like the Sun or Sirius. As you can see from the image of Betelgeuse, it's no longer a perfectly spherical object. The edge of its outer atmosphere has spread very far, making it difficult to pinpoint its outermost layer. Therefore, errors are possible. As of September 2024, the mainstream scientific view considers WOH G64 to be the largest known star. It doesn't belong to the Milky Way galaxy. It's a star in the Large Magellanic Cloud, approximately 160,000 light-years from Earth. Its radius is about 1,540 times that of the Sun, and its volume is about 4.3 billion times that of the Sun. If it were placed in the Sun's position, it would engulf all celestial bodies within Jupiter's orbit, including Jupiter itself. This star's size closely matches the limits of stellar evolution. Theoretically, the limit for stellar growth should be around 1,500 times the diameter of the Sun. Thus, its size has gained mainstream scientific acceptance. Interestingly, WOH G64 is surrounded by a dust cloud approximately 1 light-year in diameter, ejected from its outermost layer. This dust cloud is estimated to contain enough material to create 9 solar systems. Whether it's UY Scuti, Stephenson 2-18, or WOH G64, they are all somewhat bloated, possessing large volumes but relatively small masses. UY Scuti, for example, has a volume 750 million times that of the Sun, but only about 32 times its mass. G64 has a volume 4.3 billion times that of the Sun, but only about 40 times its mass. This is because they are all red supergiants, nearing the end of their lives. Stars at this stage cannot maintain both large volume and high mass, as they continuously expand outwards, losing mass in the process. The most massive star discovered so far is BAT 99-98. Its mass is 226 times that of the Sun, but its diameter is only 37.5 times that of the Sun. If placed at the Sun's position, it would be roughly half the orbit of Mercury. According to current research, this star had 250 times the mass of the Sun when it was born, and has since lost more than 20 times that mass. It is only 7.5 million years old, while the Sun is 4.6 billion years old, making it very young and highly active. It belongs to the Wolf-Rayet star class, a very special type of massive star in the universe. These types of stars have several characteristics. First, they are extremely massive and luminous. Their masses are typically more than 20 times that of the Sun, with BAT 99-98 exceeding 200 times the mass of the Sun and boasting a luminosity 5 million times greater. Second, they have extremely high surface temperatures, reaching 50,000 to 100,000 degrees Celsius. Third, they exhibit extremely strong stellar winds, reaching speeds of thousands of kilometers per second. To put this in perspective, Neptune's wind speeds are only around 600 meters per second, and such intense winds would cause them to rapidly lose mass. They could potentially lose the mass of a sun within a year. Fourth, they have short lifespans. BAT 99-98, as a typical example of this extreme type of star, evolves very quickly, with a lifespan typically not exceeding 10 million years. In contrast, stars like the Sun have a lifespan of approximately 10 billion years. It is currently 7.5 million years old, and it is predicted that soon its core fuel will be exhausted. ultimately triggering a supernova explosion, forming a neutron star or a black hole. While making this video, I saw a question online. Is it possible for a star to exist in the universe with a diameter of 1 light-year? Do you think such a large star is possible? Currently, it's impossible for a star to have a diameter of 1 light-year. Let me explain why. First, the large stars we know of, like WOH Scuti, Stevenson 2-18, and WOH G64, these red supergiants, already have enormous diameters. If we consider a diameter 1,500 times that of the Sun, that's equivalent to about 2 billion kilometers. However, 1 light-year is approximately 9.46 trillion kilometers. Compared to that, the diameter of these large stars is minuscule, only 1/10,000th of a light-year. Even if all the matter we've discovered so far were compressed together, the resulting gravity wouldn't be enough to trap hydrogen particles the size of a light-year. Second, the reason a star can exist stably is because its inward contracting gravity and outward radiating pressure are in a dynamic equilibrium. When a star reaches its red giant stage, its volume does indeed expand dramatically. However, once this expansion exceeds a certain limit, the pressure in its core becomes insufficient to support the outer layers. If a star expands to a scale of 1 light-year, the gravity of its core simply cannot control such a vast area of matter. Its outer layers would become extremely sparse, almost a vacuum, unable to maintain the star's structure. Furthermore, nuclear fusion reactions within a star require extremely high temperatures and pressures. If a star expands to 1 light-year, its core would be unable to maintain sufficient temperature and pressure to continue nuclear fusion. Without a sufficient energy source, the star would quickly collapse. Therefore, considering gravitational balance, stellar mass, and the physical conditions for nuclear fusion, a star with a diameter of 1 light-year is virtually impossible in reality. Since a 1 light-year star is impossible, are there other types of celestial bodies or structures that could reach a light-year diameter? Yes, there are. For example, black holes. The event horizon diameter of a supermassive black hole can indeed reach, or even exceed, 1 light-year. There are also nebulae. The universe is full of such gas or molecular clouds, some reaching several light-years in size or even larger. For example, the Orion Nebula has a diameter exceeding 24 light-years, and the Horsehead Nebula is also several light-years in size. Therefore, while a single star cannot possibly reach a light-year scale, other types of celestial objects and structures can indeed reach or even exceed this scale. However, our current belief that no star has a diameter reaching 1 light-year is based on existing scientific theories and observational techniques. But a core characteristic of human science is that we must maintain curiosity and continuously explore and progress. Many theories once considered the limits have been proven wrong. Therefore, perhaps a future discovery will change our understanding of the universe.